How many basis vectors do you have? You don't have just 2, I hat, j hat. You have n of those, where there are an infinite number of them. So C1 represents the projection of psi total onto the first basis. C2 equals the projection of psi total onto the second basis, and so on.
I understand what you mean by basis.
Basis, we talked about it, I talked about it last time. A basis set in vector space essentially spans two-dimensional space. Like if you have an I hat and j hat, and you had an arbitrary vector f, can you build an f as a linear combination of I hat and j hat if f is two-dimensional? So here's a two-dimensional f. Can I build it as a linear combination of I hat and j hat? Yeah. Okay. So that's vector space. How many basis vectors would you need in three-dimensional vector space?
3.
And what might you call those?
X, Y, and Z.
Or I hat, j hat, and k hat. Now, can I build any vector in three-dimensional space as a linear combination of the I hat, j hat, and k hat basis? And the answer is yes. Okay. So then what we did is we made the transition not from a vector space, but to a function space. All right, and in the function space, you don't have I hat, j hat, and k hat. You have these things. That's like the equivalent of I hat. And then for n equals 2 is j hat. And for n equals 3 is k hat. And n equals 4, keeps on going because there's an infinite number of bases.
So it's adding like dimensions to the like all together, like as summation. Like what do you consider that?
Okay, so Dino, the answer is in vector space, the minimal number of bases that you need is equal to the dimensions of your space. So if I need 3 basis vectors, I hat, j hat, and k hat, what is the dimensionality of the space that I'm living in? 3 dimensions. All right? So that's the analogy. When we go over to function space, it's a little funkier. All right? You can't really say that that's how many dimensions you have. This basically what you say is that function space needs an infinite number of these bases, an infinite number of function bases to span a function space. Again, it's this picture. This is the vector space picture. Here's a function space picture. Say I had a cosine, say I had a sine. Does the sine fill up all of, and this is function space now. Does the sine fill up all of function space? No way. All right. What about the sine of 2? The sine of 3? The sine of 4? The sine of 5? Right. So you could build f of x equals c1 cosine of 1x plus c2 cosine 2x plus c3 cosine 3x. But how many of these cosine terms would you need? An infinite number. So these cosines form an infinite basis set in function space.
Which is different though than like x.
One more second. And then when you're all done,
Yeah.
you can expand any function as a linear combination of those bases. So what do I have here? A vector space or a function space? Okay, it's a function space. How many dimensions is it? 2. Here? How many functions did I need down here?
Oh, so it's an infinite number.
There's an infinite number of those. And so I have to find the projections onto those infinite numbers. And this is exactly how a Fourier series works, Fourier integral works.
You need sine.
But you can do it in terms of sine. What you need are linearly independent functions.
Right.
And so we talk about the inner product in function space.
But that's different than I hat, j hat, k hat.
Right. It's where I'm making an analogy between the vector space and the function space. And generally speaking, if you understand the idea of function in vector space, you can carry it through to a vector.
But it's not like infinite dimensions.
Right. So that's why I said to you. It's an infinite number of bases, but it's not infinite dimensions.
Right.
But how are they orthogonal?
So they're orthogonal. So
Because it doesn't look like they're orthogonal.
So to understand orthogonal means linearly independent. Okay?
I
And this
think,
is-
like,
okay, slow down,
perpendicular.
Mike, slow down. If you want the answer, hold on.
Yeah.
Okay? So here's what, this is stuff we've already done. Okay? And so I will do it again. Okay, you ready? Vector space. I hat, J hat. Here's the arbitrary vector f equals f of x in the I hat plus f of y in the J hat. Right? So, so the first question is R, I, and J linearly independent? That means you have to understand what linearly independent means. All right? And what linearly independent means is can you get J equals some constant times I hat? Can you do that?
No.
No. All right? So I hat and J hat are linearly independent. Another way to say this. So they are not. So you can't. No. So J hat, therefore, I hat and J hat are linearly independent. All right? Another way to say this is to represent them as vectors. All right? If I represent I hat equals 1, 0, and J hat equals 0, 1, what I can do is kind of do a Gaussian elimination idea, 0, 1, 0, 1. All right? Now, if I try to Gaussian eliminate, you remember how to Gaussian eliminate? When you multiply a constant times one row, you try to subtract them to get rid of a row.
It's already in reduced row.
All right? Is there any way you could multiply a row here to subtract from here to get rid of those two ones?
No.
And the answer is no. So this is called reduced row echelon. This is from linear algebra. This is the reduced row echelon form. You start off with a general matrix, and you try to get it to reduced row echelon. When you get it to reduced row echelon, in this case I'm left with 2. So that means I need 2 basis vectors to do the problem, which identifies the vector space as how many dimensional? 2-dimensional. Therefore, this equals a 2D vector space. All right? And so when you guys go home, what you should do is try something. Try say, what if I had a new vector? What if I claimed I had a k hat equals 2 in the I hat? Right? So then what I would try to do is I would go 1, 0, 0, 1.
That's not linear
And
independent.
then I would go 2, and then 0, right? Put 2 in the I hat and 0 in the k hat. But what you realize, if you subtract from this 2 times row 1, right? So Gaussian eliminate. So if I go 2 times R1, let's do it this way. Go R3, row 3 minus 2 times R1. What does that go to? That goes to 1, 0, 0, 1, and then what happens to that row? Goes away, it becomes 0, 0. So what do you say about this row and that vector? Was it linearly independent from the other bases? No, it was redundant. It was just like the other one. So Gaussian elimination to this reduced row echelon form will tell you the minimum number of bases in the space. I'm teaching you math.
And the reason why the cosine function.
Okay, so I'm going to get there. This also has a couple other properties. In vector space, we recognize that I dot I equals what?
1.
Equals 1. And I dot j
0.
equals 0. So what is this the definition of?
Dot product.
This is the definition of the dot product in vector space.
And that's orthogonality.
Okay, let me go over here. I'm now going to go to function space. Sorry, I don't have a lot of room over here. I'll go different. Okay. Let's go to function space. All right? So, function space looks like this. Here's x, and here's f of x. What could f of x be? It could be anything. It could take up anything. All right? So, for example, I'm going to claim that cosine of mx, where m equals 1, even 0, 0, 1, 2, 3, to infinity, equals the bases. Okay, so cosine of 0 is 1, so that's 1. Right? But does that get everything in function space? What if my function looks like this? What if my function was this? That's my function. Does cosine of one term fit? Does that reproduce my function space? Does that reproduce my function? The answer is no. All right? But what if I went on to say cosine is this? Sorry. And cosine of 2, then cosine of 3, then cosine of 4, and so on.
Are you trying to cover the space?
I'm trying to fill function space. Yes. What I say here is the bases span. So I hat and j hat, they're linearly independent. It's 2D space. So I hat and j hat span 2D vector space. All right. Now going with what Dino said is therefore I claim that the summation over n of cosine mx, what I'm going to say here, Dino, is it fills functions, fx, function space. And if it fills function space, what my claim is that f of x can be built as some linear combination with appropriate chosen n constants, right, times cosine of nx.
And that's the basis for why Fourier series works.
That is why Fourier series works. Fourier series uses cosines and sines, all right, they're all linearly independent. So now let's ask some things. The cosines of nx's are what? These are the actual bases in function space. How many are there? Infinite number of them. What are these things?
Projections.
Those are the projection bases. Does that same thing work over here?
Yeah.
This just happens to be two-dimensional. This is
And
infinite.
if you multiply, get the answer different.
Okay, let's ask a
Then
couple questions.
it works just like the dot product.
Hold on. So let's ask a question. Are cosines and x's linearly independent? So for example, does cosine of 2x, can that equal some constant times cosine of 3x?
No.
All right, can you do that? Can you make that happen?
No.
All right, and they can't. And if you can't make these things like that, then what does it say about these bases?
They're orthogonal,
They're orthogonal, or that they're linearly independent of function
And
space.
if you multiply the dot
Okay, so I'm getting there, all right? So, are these bases, if you want to think about them, they're definitely linearly independent. And if you want to use this language, are they orthogonal in function space? Well, let's get to that a little bit more. We say when the dot product is 0 that they're orthogonal, right?
Yeah.
Okay, in vector space. Here's what we're going to do. So, right now we have linearly independent bases in function space. All right. Now, here's the last part, and this is the important part because we want to get Hilbert spaces, because that's the connection to the matrix formalism. All right. How can we make a dot product in function space? Do you think it's going to look like I hat and j hats, where you have this thing? Like, is there a connection where you can see an I hat and j hat, where one is like this and one is like that? Okay, it's not obvious that you can do that. All right. So the definition of the dot product in function space is called the inner product.
Yeah, the integral of one times the other is 0.
And it is the integral of like f of m times f of m dx. And it equals